Well, so you might be thinking to yourself that this whole complex number thing is really just kind of a pain. How are they getting this complex number thing? Is it just completely disconnected from reality? Well, yes and no. A complex number is of the form a plus bi, where a and b are real. A is a real part, and b times I, is considered an imaginary number. And we always express these complex numbers in standard form. It's something like a plus bi. So if I had 5 minus 3i, actually I should get a pen here. Let's try that. If I had something like 5 minus 3i, it's of that form where I have a real part separated from a imaginary part. So this is what I'm looking to do. If I'm writing a complex number in standard form, I want to have a completely separate real part and a completely separate imaginary part, and the two would be joined by an addition or a subtraction sign. So where does this complex number thing fit into the entire scheme of the number universe? Well, that's what this diagram on the left is meant to show. In this particular case, when we talk about imaginary numbers, what we really mean is that a complex number is a result of an operation. And let me just tell you a quick story right here. We start out counting when we learn algebra about natural numbers. And we know that natural numbers are the result of just starting counting with our fingers 1 plus 2 plus 3 plus 4 and so on. And we can add any two natural numbers and get a natural number result. But it doesn't always work with subtraction, because if you take a natural number minus itself, you get 0. So the whole numbers are the next logical step. Whole numbers include 0 and allow us to count from 0 onward. If we start getting negative numbers, as in we start subtracting 10 from 6 or something like that, we start getting negative integers, negative numbers, which are not in the set of naturals or wholes, so the set of integers was invented to take care of that particular issue. Well, what about division? Well, division was not included in the set of real numbers, or integers, right? Because if we divide 12 by 4, we're okay. But if we divide 4 by 12, no such luck. So we needed rational numbers to help fill that void. Well, rational numbers are fine because we can get non-rational, non-integer fractions, and we get integers that are also written as fractions when we divide them by 1. But when we started doing things like taking square roots and cube roots of numbers, we found that not all of those numbers could be considered as rational. So we had irrational numbers, and when we add the irrational numbers to the rational numbers, we get the set of real numbers. Okay, so those are our real numbers. Now the thing about real numbers is that they're good when it comes to addition, subtraction, multiplication, division, and mostly square roots. But as we saw, if we try to take the square root of a negative number, it doesn't work. And so we needed to invent imaginary numbers. Well, the so-called imaginary number is really just a form of a type of number that involves I. And when we put them together, we get what's called a set of complex numbers. So complex numbers are actually a set that includes both real numbers and imaginary numbers. Some real numbers can be considered as a complex number if we say, for example, the number 3, the real number 3 is the same thing as 3 plus 0i. So a real number is a kind of complex number with a 0 imaginary unit. Imaginary units too can be written as complex numbers, because if I had 3i, I could write that as 0 plus 3i. So an imaginary number is a complex number with a 0 real part. So complex numbers combine those together. All right, so let's go through a couple of examples where we have to write each of the following expressions as complex numbers in standard form. And 5 plus the square root of negative 20. Well, we've encountered this animal, negative square root of 20, before. We rewrite this expression so that we can simplify our radical. And whenever we see that negative, we drag that negative 1 out as a separate entity, and then we handle whatever's left. And in this case, 20 is the same thing as 4 times 5. And so when I rewrite this expression, I'm going to have 5. I'm going to be adding that, right? Notice we don't change the sign of the addition, right? The square root of negative 1 just gives us I. So we're going to have the square root of 4, which is 2, times square root of negative 1, which we carry as I, and then 5 under the square root. So 5 plus 2I squared of 5, that's a complex number in standard form. Well, you might be asking yourself, what about this next one? Isn't it already a complex number in standard form? The answer is no, and that's because the two numbers are separate, are joined together as a single fraction. We don't want that. So if we have a complex number in standard form, we always rewrite these expressions so that we have a real part and a completely separate imaginary part. So we'd say 4/3 plus 2/3 I. And yes, I write 2/3 times the imaginary unit I instead of 2I over 3. Be careful when you write this. As a complex number in standard form, we mean a real part and a completely separate imaginary part. All right, well, let's talk about this last one. How about C? Well, if we take this, we're going to get negative 1 in the numerator, and we're going to be subtracting the square root of negative 25. Well, as we now know, that's negative 1, and the square root of 25 over 5. So when we reduce over 15, pardon me, so when we reduce this, we're going to have negative 1 minus 5I divided by 15. But we reduce or simplify this by writing each of these expressions as two separate fractions. So we're going to have negative 1/15 as our real part, and we're going to have negative 5 over 15. Remember, that reduces as 1/3 I, and this would be our complex number in standard form right here. Okay, more in the next video.